All right, good evening, everyone. Again, this is Eric Silver from the Delaware Riverkeeper Network, and we want to welcome you all to tonight's riparian buffer presentation. This is the second in a series highlighting the many key features of riparian buffers and their protection. So we want to welcome folks who are joining us for the first time. We have had a previous webinar that has been recorded, and that's one of our announcements, is that this webinar will be recorded, and we will share the link with you after the webinar is over in case you want to share it with folks, or if you want to come back and listen and review any of the material. I'm Dr. Eric Sildorf with the Delaware Riverkeeper Network, and I'll be the moderator for tonight's presentation. A couple of other quick housekeeping items before we get started. The most important probably is that we want to encourage folks to type questions into the chat box. We'll likely won't get to every question at the end of the presentation, but what I'll do is I'll compile those questions, and then I'll ask those questions to Bern Sweeney at the end of the talk, and we'll try to cover as many of those questions as possible at the end. The other announcement is that we encourage folks to look for additional webinars hosted by the Delaware Riverkeeper Network. We're going to be moving into a number of key policy questions on riparian buffers in the months to come, including questions about takings, questions about legal protections for these streamside corridors. We don't yet have dates scheduled for those next webinars, unfortunately, but they will be coming out, so we will contact you with those. So without further delay, let me introduce our speaker for tonight. It is really with great pleasure that I welcome Dr. Bernard Sweeney as tonight's speaker. I've had the chance to work with and to admire Bern's research as a stream ecologist and as a leader in the field for over 25 years now. Bern is currently a distinguished research scientist at the Stroud Water Research Center and has served in many research and leadership roles at Stroud over the last 40 years. Really briefly, I really could go on forever talking about Bern's research. Bern's research has spanned many aspects of the ecology of stream systems, including population and community ecology, pollution assessment, and the role of streamside forests in their overall health and ecology. Indeed, many of Bern's and his colleagues' research publications are the most important and most heavily cited reference papers, particularly in this area of riparian buffers. So we are really honored to have him here tonight, and we really want to thank Bern for coming. So without further ado, Bern, thank you very much for sharing your time and your insights with all of us here tonight, and I will turn over the presentation and the mic to you.
Well, thanks, Eric, and thanks to everyone for taking time this evening to discuss the ecological aspects of streamside forest buffers and how streamside forest buffers can play a significant role in improving the quality of water in the streams and rivers of the United States, and for that matter in the world. But yeah, so I want to start out with a photograph I took from National Geographic that was published recently of a young lady standing in a stream in the United States, protected by the Clean Water Act, the U.S. EPA, and a bunch of local and state agencies and regulations. And just to point out that we still have some serious water quality issues in this country. I think you'd all agree, everybody that's on the line, that you would not want to drink the water out of that stream that we're looking at, nor would you want your livestock or your pet drinking out of it. I also want to show this graph of a study that was done by EPA recently, and it's the National Water Quality Assessment. And these are all the study sites across the country that were used to try to get a handle on what the current water quality level is in our streams and rivers. And the report card that came out about 18 months ago was not good. There were regional assessments of water quality, but the average across the United States, and those were not good, and the average across the United States was not good. This is basically the report card for the entire country. And the report card said that 55% of the streams in the United States were in poor quality condition, and the 23% were in fair condition. And I'm an ecologist, and I study macroinvertebrates, and from a macroinvertebrate standpoint, and macroinvertebrates are the most common animals in streams, basically being in poor condition means that it's likely that almost 70% of the species of macroinvertebrates that should be in a stream are no longer there because the water quality is insufficient. And fair condition is, 30% have been lost. And so I don't know about you, but if I woke up one morning and realized that 70% of the neighbors in my neighborhood moved away or left, I'd be concerned. And yet this report card came out a year and a half ago, and there really wasn't much concern raised by the public. But the point I'm trying to make really is that we still have a very serious issue of water quality, especially when you think about the fact that only 400 years ago, you could drink the water out of almost any surface stream in the United States without worrying about getting sick or dying or anything like that. And there's a number of reasons for this, and we're going to talk about it. But one thing, things have changed, and one thing that has dramatic change is the fact that 400 years ago, when you stood on the banks of any stream, or you stood in any stream in the United States and looked up, you would have seen this. You would have seen a canopy of forest over top of that stream. And that, of course, has changed dramatically for a number of reasons, in particular, human land use. And so I guess one of the points tonight is to reemphasize something that I realized a long time ago, and I've been at this for a long time, as Eric said. I published a paper in 1992 about the role of streamside forests in stream ecology and water quality. And in the abstract of that paper, I said the following. In this paper, I suggest that the quality of streamside forests may be the single most important factor altered by humans that affects the structure and function and ultimately water quality of the streams providing water to the coastal embayments. And at that time, the coastal embayments I had in mind were Chesapeake Bay, the Gulf of Mexico, and so on and so forth. And so 26 years ago, I realized that the removal of the riparian forest had a dramatic impact on the stream ecosystem and the water quality in those streams. And so that got me onto what we're talking about tonight, especially. And so I want to start out by thinking about what factors have led to the loss of water quality. And of course, most of them are related to humans, right? So the first thing is just people, the sheer number of people. These two graphs are from a study that we did here at the Stroud Water Research Center on water quality in the New York City drinking water system. And the top graph is water quality score of 125 different streams that provide part of New York City's drinking water. And they're arranged from left to right in decreasing order of water quality. So the dirtiest streams are to the right and the cleanest streams are to the left of this graph. And beneath that graph is the population, the human population density of each of those 125 watersheds. And you can see a clear relationship between increased human population and decrease in water quality. And that is well known and well established. The second factor really is people's mindset. In other words, the way people think about our streams and rivers. In particular, the fact that a lot of people think that small streams don't really count. If you can jump across the stream, it doesn't really count. It really doesn't matter. It's small and trivial. So in other words, this small stream, which is being polluted by a malfunctioning wastewater treatment plant of a small community, this really doesn't matter because it's a small stream, it's a small amount of pollution, and besides, look, it's flowing into a bigger stream, it's being diluted. If you were to clean up this pollution in this stream, would you be able to measure it down in the Gulf of Mexico or down in the Chesapeake Bay? Probably not. But does it matter? Yeah, because there are tens of thousands of these kinds of incidents in a given watershed that in a cumulative fashion contribute to the problem that I alluded to at the beginning of the talk, the water quality problem. And besides, 90% of all the streams in the world, all the streams in the United States or throughout the world, are streams that you can jump across. So these are really important. And these small streams are everywhere in a watershed. They interface closely with human populations. And in fact, if you were able to trace most of the pollutants in a big river back to their source, they would have entered that river system probably through one of these really tiny, small headwater streams. And so small streams count, and we can't lose track of that. And the last thing I want to talk about before we really get into the buffer discussion is people's needs. And that contributes in a big part to this water quality issue. There are 7 billion people on this planet as we speak. There's going to be 8.5 billion by the year 2025. And guess what? Each of those people need 3 different pieces of the watershed for very fundamental purposes in their life. One is housing. They need a piece of the watershed for housing, whether it be a farm or in a housing development, it doesn't matter. They need a piece of the watershed for their business activity, whether they're an attorney in a high-rise building or a Lancaster farmer running a sawmill, it doesn't matter. They need a little bit of the watershed for that. And they need a piece of the watershed to get their food. So whether it's a corporate farmer or a family-run farm, pieces of watershed are needed to produce the food for these 7 billion people. And so, we know for sure from a lot of experience and a lot of past studies that when we trade the natural vegetation in a watershed, and in most of the continental United States, natural vegetation is forest, we trade that for these human activities, for houses and businesses and food production. What really takes a hit is water quality. We know there's a big relationship there, a significant relationship. And so the burning question really, and the question that we're addressing tonight in this webinar is, can we have houses, farms, and businesses and still have clean, fresh water for humans and wildlife? And, my answer is yes. And it's not because I'm an optimist or because the glass is always half full for me. It's really because I firmly believe that we have the wherewithal and the technology to use our land in the way that we need to use it, but still have access to clean, fresh water. There is a caveat, though, and that is that, yes, we can do this if we make some changes in how we go about our housing, our farming, and our businesses, right? So one of the most simple things that we need to change is we need to create a little space between the danger of what we're doing as humans and what we're trying to protect as humans. And so to drive this point home, creating a little space between the danger of what we're doing and what we're trying to protect, I often use this analogy in my workshops, and it works pretty well, and I'm going to try it on you. This is my power saw that I keep in my garage. This is my left hand in that picture. And I ask you the question of how is it possible for Bern Sweeney, a biologist by training, an ecologist, a nerdy scientist as my wife might say, how is it possible for me to take this thing out of my garage on a Saturday morning and use it for 4 hours and not cut my fingers off? Okay? But I've done that, and I've done it a lot, and I have all my fingers. And the answer is that it's designed into the instrument, right? It's part of the design. The danger of what we're doing is right here, this sharp saw blade that can cut my fingers off in an instant. What we're trying to protect is my hand, right? And the way it's designed and increases the protection from the hand is to put a little space between the danger of what we're doing, the saw blade, and my hand. Now, it's only 2 or 3 inches, but obviously it's sufficient because I still have my fingers, right? And then we put something in that space that makes the space even more effective at protecting my hand. And in this case, it's this metal shroud that we put in. So we create the space and we put something in the space that will make it more effective at protecting what we're trying to protect, right? So the same thing holds for the environment and for environmental situations. What's the danger that we're doing here in this photo? It's growing corn. Now, some of you on the webinar may be farmers, and you're saying to yourself, no, Bern, growing corn is not dangerous. But look at that corn. Look how tall that corn is. Look how weed-free that corn is. We use chemicals often to grow corn that tall and that weed-free, and to be that productive. I often say to my farmers in my webinars, we're using atrazine in this situation on this corn, and if I had a gallon jug of water here and put 8 ounces of atrazine in it and offered $500 for any of you to come up and drink that atrazine, would you do it? And the answer always is no. Of course not, because I'm going to get sick. I'm going to probably die because it's toxic, right? It's not good for you, and it's toxic to humans. Well, what are we trying to protect here? We're trying to protect this little stream right here. Because if you follow the stream 7.5 miles downhill, it ultimately becomes the water source for residents of Newark, Delaware. And just as no individual in this webinar or no farmer or anyone would want to drink atrazine out of a gallon jug that we put on the desk, we don't want residents of Newark, Delaware drinking atrazine because of farming activities uphill, right? And so there simply isn't enough space between the danger of what we're doing, growing corn, and what we're trying to protect to imagine that what we use on this corn is not going to get into this river system. So we need to push the corn back. We need to create the space, and we need to put something in that space to make it more effective. We need to push it, and we're going to talk about that tonight. How far do we need to push it back? What do we need to put in that space to really make it very effective? Here's what we're trying to do. We're trying to produce milk. We're trying to produce beef. There's no space here. These animals are in the stream. And this stream itself is also a source of drinking water for humans. And so there's not enough space here. There's simply no space here. And there's no space here between this housing development and this stream. So we need to create the space, regardless of what the human land use is, whether it's farming or housing or whatever. And we need to put something in that space to be more effective. And what I'm going to argue with you tonight is that we ought to put trees in that space, because trees make that space more effective at doing what we want it to do, and that is protect the quality of the water in those streams and rivers. Okay. If that space that we create falls between the stream and the human land use, we call it a streamside forest buffer. So that's kind of what we're talking about tonight. And we refer to a streamside forest buffer as a best management practice because it's the best thing that we can do with that piece of land between the stream and whatever we're doing on the landscape. It's a BMP for that parcel of earth. So what is a good simple definition for a streamside forest buffer? Let's start with this one. It's a best management practice, a BMP, for keeping pollutants out of streams. And when I make this first cut of the definition at my workshops that I put on, everybody nods their heads and say, "Yep, that's it. That's what we've been talking about. Yeah, streamside forest is a best management practice for keeping pollutants out of streams." And then everybody's appalled when the next slide I put up looks like this. It says, "Not quite right. That's not quite it. That's part of it, but it's not there." Yes, it's a BMP for keeping pollutants out of stream, but equally important, and maybe even more important, it's a best management practice for improving the health of the stream itself, of the stream ecosystem, so that ecosystem can actually process any pollutants that actually get into the stream. And I'm going to show you in a few minutes that although we can try to keep things from getting in the stream by putting streamside forests up and by other kinds of best management practices, we can't keep it all out. So we need to have this sort of two sides of the streamside buffer approach. We need to view the streamside forest buffer as being a system that will keep things that we need, that are byproducts of human activities on the landscape, from getting into the stream. But we also need that streamside forest buffer to help us improve the habitat and the quality of the environment in the stream itself, so that we have a highly functional ecosystem there, so that if anything gets past our buffers and our other BMPs, the stream itself can actually process it and keep it from moving downstream and causing problems with our drinking water intakes, with our downstream estuaries, and so on and so forth. So there's this two kind of sides of a buffer that we need to consider here. Let's start with how well does a forest buffer keep stuff out of the stream? And the answer to this is probably going to be unsatisfactory to you. The answer is it depends on how wide it is, but that's what the science is telling us. Tell me how wide the buffer is, and I can tell you how well it's going to do on whatever front we're talking about. This is a graph from a technical paper that was published 2 years ago, and I think illustrates this point pretty clearly if I can work through this with you. So this is a graph of removal efficiency of atrazine on the y-axis, so removal efficiency of atrazine as a function of width of the buffer or distance of trees from the crop to the stream, to the river. And the graph shows that if you create a space, a narrow space, and put trees in it, you get about 40% removal of atrazine. But if you greatly increase the width of that space to almost 200 feet and have trees in it, you get almost 100% removal. And if you create those same kind of spaces and put different vegetation in there, if you put shrubs in it, you still get removal, and you get more removal with more distance, but you don't get as much as with trees. And if you put grass in it, you even get less. So this illustrates that what we put in that space really does count, and that, again, I'm going to argue with you that trees are what we should be putting in there, not only because of this study, but because of other things that we're going to talk about that show that trees really make a big difference in terms of removal of this stuff and increasing the health of the stream ecosystem. Well, 4 years ago, a colleague of mine, Dennis Newbold, and I took the time to review a bunch of studies, in fact, several hundred studies, that dealt with this issue of how wide should the forest, streamside forest be, and how much can we get out of it if it's a given width. And this was, tell you, a thankless task, but I'm glad we did it now. I wasn't glad we did it when we did it, but we did it. And I want to share with you some of the results of that study. Let's talk about sediment. Now, sediment is one of the most important pollutants in the United States, in the world for that matter. It was identified by that EPA study as being one of the #1 things that we need to address, right? So sediment is, it comes off of the landscape. It causes the streams to look like chocolate milk when it's raining, and it's a big problem for water filtration plants and so on and so forth. This is actually a graph from that review paper that we published, and it shows sediment removal efficiency on the y-axis as percent, so from 0 to 100% sediment removal efficiency, as a function of how wide the streamside forest buffer was. And each of the data points in this slide are individuals' published studies. And so, for example, this data point is a published study by a group of scientists who studied a 35-foot wide buffer and found out that it was able to intercept about 20% of the sediment and keep it from getting in the stream. Whereas these two studies were two independent studies by two different sets of scientists that studied a 200-foot wide buffer and were able to show that, yeah, a 200-foot wide buffer kept about 90% of the sediments from getting in the stream. So this is a lot of studies and a lot of data going into this graph. And then, of course, we fitted a line to the data to try to depict what the average outcome is for a given size buffer, a given width of buffer. And so when you use that fitted line, you can see that if the buffer is 35 foot wide, you get about 64% of the sediments trapped. If you increase it to 100 foot wide, about 84%. If you increase it to 200 feet wide, it's about 90%. Now, when we got these results at the first time, it was a head scratcher for us, I'll tell you, because we're looking at it and we're saying, wow, we get a lot of bang for 35 feet. Wow, we get 64% of the sediment being removed. But we add another 65 feet and go to 100, and we only increase it from 64 to 84%. Then we add another 100 feet, and we only increased it 6%. And it said to us initially that, geez, maybe we should just stick with 35 feet because we get a lot of removal, and that's easy to sell, right? That's easy to convince the public to do that. But when we drilled down on the data harder, we realized that what we were trapping in the first 35 feet were large particles of sediment, like sand grains. What we weren't trapping were the particles that really make a difference to water quality and to the kind of particles that interfere with aquatic life. And those are the silts and the clays, the really fine particles. In order to trap them, we needed 65 more feet of trapping space. So basically, what we got in going from 35 to 100 feet was, only 20% more sediment removal by weight, but we removed the major pollutants that were causing problems for our streams and for our water treatment plants, right? And if we just promoted a 35-foot buffer in terms of sediment, we wouldn't be making much progress in water quality. So that's the key point here on that graph in our review. Let's look at nitrogen for a second, and just briefly. Nitrogen, we have the same kind of graph. This is nitrate removal efficiency on the y-axis as a function of how wide the buffer is. This is in meters, but the point of this graph really is that these are each individual published studies. Again, a lot of data going in here. And the point really is that the wider the buffer, the more nitrogen we're getting removed. 20% with a 35-foot buffer, 48% with a 100-foot buffer, 75% with a 200-foot buffer. The wider the buffer, the more nitrogen is removed. So, it depends on how wide the buffer is and how much we're going to remove. Can we improve the effectiveness of a riparian forest buffer in terms of its removal efficiency or its effectiveness for sediment, for nitrogen, things like that? And I think the answer is yes, we can. And we think that by adding, in conjunction with a streamside forest buffer, something called a level lip spreader to its design, we can make some improvements. Now, level lip spreader, there's a phrase that I'm sure that 95% of you on the call have never heard before and are scratching your heads what the heck that is. But let me try to explain it to you briefly. This cartoon shows a stream, it shows an agricultural field, and it shows where someone has put a streamside forest buffer in place between the stream and the field to try to intercept sediment, nitrogen, and so on and keep it from getting in the stream. We think we can improve the efficiency of this buffer and this system of keeping stuff out by adding a swale in between the human activity and the buffer itself, so right in here. And so that would look like this. So it would be excavating a shallow swale, maybe a half a meter deep, that if you have surface runoff during a high rain event, and you actually have surface runoff of this cornfield, instead of that runoff, which is laden with perhaps sediment and nutrients and things like that, instead of that runoff going directly into the stream, it would fall into the swale and get trapped there for a moment. And as long as the storm isn't too big, it'll just stay there until it seeps in the ground and moves towards the stream. And so you can imagine that if you do this, you can catch a lot more stuff moving from the fields to the stream. So this is actually a photograph of a site where we've created a 100-foot wide forest. So these are tree shelters, and these are young seedlings that were planted. The stream starts right here, and it moves to the left. So it actually is starting right there. And we've created this 100-foot streamside forest. We planted it around it. And then we've put this swale around here, and we call it a level lip spreader because the lower lip of this swale, which is this right here, is exactly on the contour, so it's level. So the level of the lip here is the same as the level up here. And the reason for that is that if you have a big rainstorm and this swale fills up with water and spills over, it will spill over evenly along its entire length and won't erode the spreader, right? And so runoff comes from this field, gets caught in the spreader, and then eventually, if it's a big storm, will spill over, but in most 85 to 90% of storms, it will just stay there, and then it'll seep into the ground. And if it's sediment in the runoff, the sediment will stay in the spreader, right? So nothing goes into the stream. If nitrogen, the dissolved nitrogen in the water will seep into the ground, and then as the water moves towards the stream in the soil beneath the forest, it will be removed through a process called denitrification by soil bacteria. And so we think that intercepting the surface runoff this way greatly helps the streamside forest buffer be more effective in its role. And so we did a 25-year study on this, and we published that a few years ago. And basically, in this particular study that we did, we were able to show that for nitrogen, we were able to remove 26% of the nitrogen. Now, 26% may not seem like a big number to you, but it's a big number. If the stock market goes down 26%, it's a big number. People get excited about it. We were excited about this when we saw that a 10-year average, we were getting 26% of the nitrogen being removed. But to me as a scientist, when I saw this, I was excited about 26%, but to me it was a good news, bad news story, because it said to me that the good news is we've got 26% of the nitrogen being removed and kept from going into that stream. The bad news is that 74% of the nitrogen is still getting in the stream. And at that moment, when we got these results, we realized that we need to think about these buffers in a different dimension. We need to think about what they can also do for the in-stream part of ecological processing, because a lot of this stuff is still going to get into the stream. And if we had the stream itself removing some of this nitrogen, or removing some of the sediment, or removing some of the PCBs or whatever, then we could do a better job of keeping it from moving down into our embayments and our estuaries and our Gulf of Mexicos and so on and so forth. So that was got us thinking about the other dimension of streamside forest buffers. So we need the stream to do a lot of work with. So this pollution is getting into this bigger stream. We need this bigger stream to be able to act on that pollution and to keep it and degrade it, sequester it, or just process it and keep it from moving downstream. And if by putting a forest buffer on this bigger stream helps that stream do it, we should do it. And in fact, that's the case. It will increase that activity. Now, we've known for a long time that a stream that has trees on its banks is better able to process stuff than a stream. So a stream like this with a forest on its bank is better able to process stuff than a stream that looks like this, that has a buffer, but instead of having trees in that buffer, it has grass in that buffer. That this situation is not conducive to having a stream that will be able to process pollutants as effectively as that previous situation where we have trees on the banks. Okay? We've known that for a long time. Another way of showing this is that if you have a small stream and it's deforested like this, I'm going to go through in the next couple of slides why this particular stream channel is not as effective at processing materials that maybe come off of these farm fields as this particular stream, which has a streamside forest along it, but maybe also has a farm field just 100 feet from it. Okay? It's a big difference in the processing ability of these two situations, and the question is why. And the direct answer, the short answer, I'm going to give you first, and then I'm going to give you the reasons behind the answer. The direct answer is that a small forested stream is better able to process stuff because, one, it has more ecosystem, and processing of these materials is done by the ecosystem, has more ecosystem per unit length of stream, and the ecosystem in a forested stream is healthier. So if the ecosystem is doing the work, you have more workers, and if the species in the ecosystem are doing the processing, and those species are healthier, then we have more workers and a healthier working system, and we just have more processing going on. So let's take a look at that. So we did a study about 15 years ago, a little bit less than that, where we actually compared. This is a piece of the Pennsylvania landscape, and Pennsylvania is no longer Penn's Woods. It's no longer one big forest. Forest occurs in patches, and streams flow in and out of forest patches. And so we said, if we really want to know whether the presence or absence of trees makes a big difference in the ability of a stream to process stuff. We really go out to a situation where we have a reach of stream like this with no trees on it and compare its ecosystem and its ecosystem integrity and its ability to function and process things with a piece of stream that's right next to it, has the same amount of water in it. In fact, the stream is flowing this direction, that has trees on it. So has trees, no trees. Let's study the bejeebers out of that pair of stream reaches and see what we find. And let's do that in 20 or 25 streams and see what, on average, we look at. So let's take a look at what we saw. And it was very profound. This is one of our study sites. This is a photo of a stream. I'm looking downstream. The stream is about 18 feet wide. It's flowing through a forest. And I'm taking this photo standing at a post and rail fence, and I'm looking down into the forest, looking at the stream flowing away from me. And the next photo I show you is I turned 180 degrees around, and I took a photo of where this stream was coming from. And it looked like this. Okay, it's coming from a deforested pasture, horse pasture. And the difference is spectacular, right? I mean, the stream here is 18 feet wide, and the stream here is a foot wide. Nobody on the webinar tonight can jump across this stream, and everyone in the webinar tonight can step across this stream. And the reason the stream is narrow, much narrower than it was in the forest, is because of the lack of forest. The lack of forest, there's increased sunlight. These herbaceous grasses proliferate. Herbaceous grasses put their roots out into the water. They form, the roots get very dense. They collect sediment. They form sod. And you take an 18-foot wide forested stream, remove the forest, grow the herbaceous grasses, and the sod on both sides of the stream encroach on the stream, and the stream narrows up very quickly. So you can go from an 18-foot stream like that very quickly to a foot-and-a-half stream in like 3 or 4 years. Okay. The good news is that this process is reversible. So if you plant trees here, the trees get bigger, they shade out these grasses, the stream will re-widen to its 18-foot configuration, and that'll take about 10 or 15 years to do that. Okay. Now, you're asking yourself, what difference does it make if a stream is narrow or wide? You know, who cares about that? Well, it turns out that it's a big difference in the ability of a stream to process stuff. Remember I said that the processing of materials in a stream is done by the ecosystem. And in streams, the stream ecosystem is on the bottom of the stream. It's associated with the bottom. It's not up in the water column like in lakes, estuaries, or the ocean. It's on the bottom. And so the ecosystem we're talking about, you know, are the algae, the bacteria, the fungi, the macroinvertebrates, the fish, so on. All those players are on the bottom of the stream. They're feeding. They're going through their life cycles on the bottom of the stream. So the more bottom of a stream you have, the more ecosystem there is, and the more ability there is to process stuff. So it's not hard to understand that when a stream is narrow because it's deforested, it has less bottom area per unit length than when it's forested and is much wider. So this forested wide stream has a lot more bottom area per unit length than the deforested counterpart. So this stream up here has a lot more ecosystem per unit length to do work for us. And that's the point, and that's what we observed in the study, that forest streams can do a lot more work for us. The players in the ecosystem, the bacteria, the fungi, the macroinvertebrates, the algae, and so on, are healthier in a forested stream because the conditions of a forest stream are more natural. Remember earlier in the webinar that forest is the natural state, that streams throughout the United States, especially small streams, in their natural condition were flowing through a forested landscape. And we've removed that forest for a variety of reasons. And so things like channel stability, temperature, light, food, those are more natural conditions of those things in a forested stream. And so when we did this study and went out and looked, we saw that in some of our study sites that were forested, the banks of the stream looked like this, and that if this stream, if we got a big rain event and the stream became bank full, the banks did not slough in. The stream was very stable, and when the storm resided, the banks were right where they were before the storm. But in our contiguous counterparts that have no forest on them, when the banks of this stream become full, bank full with water, they slump in, and the stream is actually moving across this floodplain a lot more quicker without the trees in this situation. So this stream is moving this way, and basically at the rate it's moving, probably in 5 or 7 years, the entire stream will be here as opposed to over here. And that's a very unstable situation because in terms of creating a really good ecosystem. Forested streams are much cooler than deforested streams. They're shaded, right? They're shaded. That's a no-brainer. And a lot of the species that live in streams that are doing this work for us like to be cool, especially in the summer, right? They have very careful requirements about temperature, especially during the warm months of the year. There's summer cool species, things like brook trout and mayflies and diatoms. This stream is just too warm. There were no streams like this historically. All streams were shaded, and this stream is probably 10 degrees way too warm, and a lot of the species that would normally live there can't live there because it's too warm. And there's too much light in that stream. How can there be too much light in a stream? Well, there can be, because the species of algae that live in streams are adapted to shaded conditions, and they want to have shaded light conditions. And they don't do well under high sunlight. Just like ferns do not do well out in the middle of a field. They need to be grown under a forest canopy. That's true of the really good algae in a stream. So when you create a small stream with no forest on it, you get a lot of this kind of algae growing in it, this long, stringy, blue, green algae, and it can dominate and become very abundant in the stream. And the reason is that nothing eats it, basically. We've done studies on this, and we've shown that the animals like this mayfly that make their living eating algae in a stream, you give them this long, stringy algae, and they crawl around on it, and they look at it, and they taste it, and this and that, but they don't eat it, and 3 or 4 days they just belly up and die. Why they don't eat it, we don't know, but they don't. What they prefer to eat is the kind of algae that you grow in a small shaded stream. So you pull a rock out of a small shaded stream like this, and it looks slippery and slimy, but you really can't see any algae on it, like that long filamentous stuff. But if you scrape that rock and put it under a microscope, you see literally tens of thousands of these small microscopic plants that these animals love to eat, and they eat them voraciously, right? And so we're growing the wrong kind of a food when we remove the trees from along a stream. And last but not least, trees along the banks of a stream can provide a lot of food directly to the ecosystem in the form of leaves. Look around your neighborhood streams right now at the fall of the year and see what's in them. And you'll see, if there's forested, you'll see tons of leaves falling into these streams. And these leaves just don't fall in the stream and then float down to the local bay or the ocean. They get caught behind rocks, and they are immediately colonized by a whole array of animals and bacteria and microorganisms that degrade those leaves and use them for energy, and really are the heart and soul of the ecosystem. And so they do a great job, and they can process these things. And so you go back to one of those streams with all those leaves in it in October and look at it in March, you don't see any leaves. Not because they floated away downstream, because they've been eaten. And so when you have a stream like this with no forest along it, it doesn't do well at processing pollutants because it doesn't have much ecosystem. It tends to be narrower, significantly narrower and less bottom area than its forested counterpart. It tends to be too warm. A lot of the species that would normally be there helping us process pollutants aren't there because they've been polluted out by the warm temperatures. It doesn't have the right kind of food. It's not growing the right kind of algae. It's not being subsidized by leaves, and so on and so forth. There's a lot of different reasons. Whereas this stream is wider, has more ecosystem, and it has the kind of conditions in it of temperature, food, and all that is conducive to having a really strong and healthy ecosystem. And there's a significant difference there, and that's why. So we need a forest along each stream. I mean, the scientific studies are irrefutable that we need to have a strip of forest along our streams and rivers. The question is how wide, and I'm almost finished here, so just bear with me. I go back to that study, the review study that we did, and that was really the purpose of that study, was to try to figure out, how wide does this streamside forest need to be in order to protect the physical, chemical, and biological characteristics of a stream. We looked at a lot of different factors in that review. How does the width of buffer affect fish? How does it affect macroinvertebrates? How does it affect sediment trapping, nitrogen processing, and so on and so forth? And when we looked across all those factors, our overall conclusion was this, and this is the concluding statement of that review. Overall, a streamside forest buffer needs to be 100 feet wide in order to protect the physical, chemical, and biological integrity of small streams. And yes, 100 feet is a lot of land. But this is what the scientific data are saying. There is no safety factor built into this. What do I mean by a safety factor? I mean that, when engineers design a bridge and for human use, they figure out the strength of materials that are needed to keep that bridge erect and keep it from collapsing and killing people. And then they take that calculation and they multiply it by 2. They double it. And that's called building in a safety factor. And we don't do that typically in environmental business. And it hasn't been done here. So 100 feet is what the data were saying. We didn't say 100. The data came out said 50, but we're doubling it for a safety factor. 100 is what it came out to be. But it's interesting that we build in safety factors for things like bridges because we don't want a lot of humans being killed because the bridge collapsed. But we tend not to build in safety factors for when it comes to environmental best management practices. So we don't say, well, the science is saying 100 feet, we ought to have it 200 feet. No, we don't say that. In fact, what we say is 100 feet, that's a lot of land. What can we get by with? Can we get by with 75? Can we get by with 50? So I just leave you with that thought, and and the science is saying 100 feet, and so that's where we're at right now. I want to thank everyone for taking the time to listen to me rant and rave about streamside forest buffers, and to try to convince you that that it really is important that we return to the days of old when you could stand on any stream bank in the United States and you could stand in any stream in a river in the United States and look up and see this and see a forest canopy over it. Because if we do that, I think we'll make dramatic strides in improving the quality of water in our streams and rivers. Thanks again for listening. I really appreciate it.
Well, fantastic, Bern. I think that if we didn't have everybody on mute, there would be loud applause all around. Fantastic presentation, really stimulating. We've got some good questions coming up from it. But first of all, let me just start by saying thank you. Really great to see both your own research and some of the results that you're summarizing from other people's research that are really valuable, kind of both on the science side of things and on the policy side of things. Some of the questions we're getting, Bern, are starting to delve into some policy questions, and so I don't know that we're going to go deeply into that now. That could easily take another half hour, an hour, and those will be the focus for future webinars. And I think we're going to have, we're getting a bunch of thank yous coming in from everybody on the chat box. There were a couple of quick, simple questions first, Bern, that I wanted to throw out before we get into a couple of the meatier questions. So if I could throw those out first. One of the questions is whether a buffer needs to be 100 feet on each side or just on one side of the stream, or is it only 50 feet on each side, and so it's 100-foot total? Kind of an interesting, somewhat technical question, but really important, I think, as we think about policy and as we think about implementing your ideas.
Yeah, so the answer is it's 100 feet on one side of the stream. So it would be 100 feet on one side and 100 feet on the other side is the way the how the review came out. Yeah, you need 100 feet.
Yeah. Right, and that's something that I think we've seen also, and I think is one of the things that at the Delaware Riverkeeper Network is a focus for our advocacy, is that it's not just that you can have it on one side and you get all the benefits, or you can split it in half and do 50 feet on each side and you get the full benefits. My understanding also was that it's 100 feet on each side. So thanks for clarifying that. A second question that I think you partly addressed is that you mentioned it might take 10 to 15 years if you reforest a stream for that stream to re-widen back to its normal width. But the question was, if you took and deforested a stream, how fast does it actually narrow up? How fast until it's encroached with grasses and things?
Yeah, in small streams, by small I mean like first, second, third, fourth order streams, the narrowing process is very rapid. Very rapid. You can take a stream like a third order stream like I showed that's 18 feet wide and deforest it, and it will narrow up in 3 to 4 years. It will be as narrow as I showed you. It happens very rapidly. Those grasses grow their roots very quickly, and the roots trap sediment that are coming down the stream, form sod, and the process goes very, very quickly. So yeah, it's a really quick process. Yeah, that's a little bit scary, right? That in one direction you can lose all that ecosystem, all that area relatively rapidly, and it'll take a fair amount longer. Although 10 to 15 years isn't forever. That's a reasonable time frame for getting it back. But certainly that's right.
Not
yeah.
that.
And I think I always say that we've taken 150 or 200 years to put the stream in the poor condition that it's in. So to say that we can turn it around in 15 or 20 years, that's not too bad.
Yeah, right. We had a little bit deeper, more kind of nuanced question about the kind of functional diversity of the arrangement of multiple species in a forest buffer, and a question that we were asking here at the Delaware Riverkeeper Network among ourselves as you were presenting is, you mentioned the value of forests, the value of shrubs, and how grasses themselves don't provide as much benefit, mixing that up together. But part of the question also is, mixing that with some of these kind of agriculturally important species, kind of multi-layered riparian buffer, including things like fruit trees and nut trees. And so that's kind of an interesting question about that diversity of species there. And a related question that we actually had some discussion in the chat room about is recommendations on individual trees or different kinds of trees, different functions of trees. One person pointed out that invasive species likely don't provide all the benefits that a native riparian forest like maples and sycamores might provide. So kind of a big question there, Bern, that you might be able to answer at multiple levels. Yeah,
so I think, I confess that one of the first buffers that I put in a long time ago in the 1980s had only 3 species of trees in it. And I'm almost embarrassed to say that now because we know a lot more. But having a bunch of species is important for a variety of reasons. I always say that you need some of the tree species in the buffer for the stream itself to stabilize the banks and providing the right kind of food for the stream and its stream organisms. You need some of the species in the buffer for sort of the terrestrial ecological aspects of the whole thing, and having the right kind of ecosystem out there for a variety of purposes, and for increasing, food for pollinators and things like that. And then you need some of the species in trees for the landowner. You need the landowner to be happy. You need landowners to feel good about the trees that they're putting in the buffer. So there's a whole bunch of reasons to have a whole bunch of different kind of species of trees in the buffer. So typical buffers now have 12, 15 or more species in them. And yeah, I did say, the data, like that one graph I showed, that trees did a better job than shrubs, they did a better job than grass. But one of the studies that hasn't been done yet, and we haven't shown, is what happens, how much, we don't really know how much you get when you add all those together. We have the right kind of understory, or the right kind of shrub layer, or the right kind of overstory, like how that all works. And so we're still doing a lot of research on these buffers and how we should manage them, and we really don't know much about the understory and what role the understory plays in the whole dynamics of a streamside forest buffer in terms of water and habitat quality. The shading, from a temperature standpoint, it probably doesn't matter whether it's, an apple tree or a maple tree or an invasive maple tree versus a native maple tree, because shade is shade, right? But from a nutrient perspective and from, like leaves for food for the ecosystem, it's really important. Like we did studies a number of years ago that showed that like species of invasive plants like multiflora rose and Oriental bittersweet and other invasive plants, those leaves were not as palatable and as good of food for organisms as the native species. And so there's kind of these kinds of things that we need to take in consideration. I sort of decided a long time ago, based on the data that was at hand, that we really needed to move away from using any kind of ornamental invasive plants or non-native plants in our riparian forest buffers, because native was what I saw as being a good driver of the kind of ecological benefits we were getting from the buffer. But why can't we have a mix? I don't see if we have a 100-foot wide buffer, there's no reason why the first 75 feet or something can be native, kind of the typical overstory plants, and then the outer parts of it may be fruit trees or something like that. We don't know how that will work, but I don't see any logical reason for arguing against it. So I think there's room for all that.
Sorry, I was muted there for a sec. That's a really good point, and I think that's something that we see in Pennsylvania is part of the emphasis of some of the grant programs now, where they're trying to look at that simultaneous benefit, like you were emphasizing, Bern, of both economic benefits to the landowner, farmers, other folks who are trying to actually perhaps harvest some kind of economic value out of part of that riparian buffer, and then transitioning that to a purely native buffer in there. So that is something that I think we're seeing, which is great to see.
Yeah.
One possibly simple question, although it probably depends on your answer, Bern, before I get into a pretty big question. We are getting close to 8, and so let me make a quick announcement that yes, we did record this, and we will share the link with everybody. So for those of folks who have to cut out right now at 8 o'clock, we will share the webinar and the link for this, as well as Bern's slides. So if you want to see those. But the first question, Bern, as we go a little bit past 8 here, and I think I mainly see 2 more questions, is what happens when the level spreader reaches capacity? So as that level spreader starts to fill with sediment, how much maintenance are we talking about?
Well, if it filled up with sediment, you can easily and probably pretty cheaply dig it out and put the sediment back up on the hillside, spread it on the hillside. But in our experience, like actually the photo that I showed you of that newly created buffer and level of spreader, that was a photo from 1990, and so that spreader is now 28 years old, and we've never had to clean it out. Now the hillside that I showed there, that's in farming and has been actively farmed in corn and beans for a long time, is under a best management practice, and so it's terraced and has waterways and so on and so forth, but it has been actively farmed. So it's not like it's not a poorly farmed farm. It's a best management practice farm, but still it's been actively farmed for 28 years, and we have not had to clean it out yet. And it doesn't seem like we're even close to it yet. So they can hold a lot of sediment, and but they also can be overwhelmed. But yeah, we don't envision a whole lot of maintenance if in fact you view these things as part of a system. And so we never want to put a streamside forest buffer in, even if it has a level of spreader, and say, okay, all bets are off, do whatever you want in terms of the farming activity uphill. We always view it as a system. In other words, the buffer and the spreader and the terracing and the waterways and the cover cropping, and all part of a system. And so all that taken into account is part of what we want to drive the land use to. But yeah, the maintenance hasn't been high on that.
Yeah, that's great to hear, Bern. But adding some of the nuance there also. So there are a couple more questions coming in. One of the questions that we saw early on, Bern, and this has a lot of policy levels, and so it might be better to focus and ask you to narrow in on the science question, is that a number of people on the webinar are concerned about the linear infrastructure that is expanding in the Delaware Basin and regionally, partly from the Marcellus Shale and as the Utica Shale formations get developed. And people recognize that kind of linear infrastructure really obliterates that riparian forest that you're talking about when it crosses streams, and it crosses not just one or two streams, but over and over and over. It crosses many streams, and there certainly are a lot of big policy questions there, things that we focus on here at the Delaware Riverkeeper Network, and partly that we're going to continue to focus on with our later webinars. But more narrowly, Bern, I think there are some really important and legitimate questions about whether a 50 to 100 foot interruption of that riparian forest causes immediate changes, how severe those changes are. Any thoughts about that and the linear infrastructure?
Well, I mean, there is the ability to have this linear infrastructure across streams without cutting through the stream. They can go underneath the stream, I believe. It's more expensive and that sort of thing, but maybe that's what we need to be thinking about. Now, the ability of a stream to recover from, an insult like, cutting through, making a 50 to 100 foot wide cut through a stream. Streams do recover from that, but it takes a long time to recover from that, and there is, in some cases, a possibility that they'll never fully recover from that because of the way the stream bed has been disrupted and the flow of the subsurface flow of water and so on and so forth. And so I think the best thing to say is that we don't know what a large cumulative effect might be if you have a whole bunch of these kind of crosses in a given stream system, but I can't help but think it's not going to be good. And that if there is an alternative way of getting linear infrastructure across from one side of a stream to another without cutting through the stream, then that should probably be the preferred method if we can.
Yeah, really big questions there about trade-offs and the costs, and then we've seen with the Mariner East pipeline some of that directional drilling has actually backfired and contaminated wells. So from our perspective at the Delaware Riverkeeper Network, even some of those actions to try to avoid the local damage have actually led to broader damage, and certainly there are the really big questions of whether it's appropriate to, and I won't ask you to comment on this, Bern, but whether to continue to invest in and expand the infrastructure for fossil fuels. When we see reports like we've seen recently of how dire the climate change implications are for continuing to invest in these fossil fuels and not make the switch. So yeah, really big questions there.
Another point, Eric, is that we're, as I pointed out in the beginning, we already have a serious issue with water quality and ecosystem health in our streams and rivers in the United States, and so at a time when we're trying to repair some of the insults of land use past, if we can avoid more insults, then we should clearly do that.
Yeah, right. There are a few more questions, Bern. There was one question that I was particularly interested in, so if I could indulge you for one more question now that we're pushing towards 10 minutes, Bern.
Sure.
There was a question that I'd never thought about, but I think it's a really important question for people that are involved in this idea of restoring these riparian buffers, which is what preparation do you advise for damaged and compacted soils for streamside buffers, right? So that if these are formerly farmed areas or there are buyouts along streams, kind of repeat flood areas where there are homes or some kind of infrastructure that gets repeated flooded and we move it out of the way, what kind of preparation do you think is advisable, or have you looked into that or seen papers on what's needed there, or how resilient are these systems to recovering even without kind of intensive preparation of those areas?
I mean, a big part of the preparation is to make sure is to eliminate any of the invasive non-native plants from the site before the forest is planted, and also if the area has been farmed for a long time, sometimes there's a real the microbial community in the soil is really depauperate, and sometimes you have to supplement the microbial community, sort of kickstart it with a supplement at the time of the planting of the seedlings, for example, if you're planting trees, with something that you would put in amongst the roots that will help it help restore some of the native flora and help those species along. But basically the main thing is to take the time to prepare the site in terms of making sure there's nothing in the site that's going to compete with the plants that you're putting in the site, and then taking the time post-planting to control the vegetation around each seedling so that you don't get the seedlings overrun by non-native plants or invasive things, and also to protect the seedlings from herbivores like deer and mice and voles and rabbits and things like that. And in our experience, we know that it doesn't happen naturally anymore. In other words, if a landowner decides to, yes, I'm going to restore the streamside forest along my stream, I'm going to stop farming it, I'm going to move it back 100 feet, you can't just walk away and it will happen on its own like it might have done 200 years ago. There are just too many non-native plants and other kinds of factors that affect it. You have to be proactive. You have to be proactive about planting what you want in there and protecting it for several years. And we recommend 3-4 years of protection. And a lot of the federal and state programs that are helping to subsidize landowners to create these streamside forests are now including subsidies for that taking care of those plants for several years after planting, because the level of success goes up dramatically with the amount of care that you put into the planting, both pre and post. And so, yeah, it's really important, and that's, it costs a certain amount of money to buy the seedlings and all, but if you don't put the time and effort into the pre and post planting, you might as well throw your money away because the success rate is going to be really low. But we typically have success rates of like 85-90% of the species that we plant are successfully creating the forest. Whereas, 20 years ago, it might have been as low as 10% or 5% because we just didn't know what we were doing. But we know what we're doing now.
Yeah, fantastic. Yeah, that's really good to hear. Well, again, Bern, we are now at 8:10, and we still do have a number of people that are with us. There are a few more questions, but I think it's a good time to wrap things up. To thank you again for sharing the stories, for translating the stories and translating the science so effectively for all of us. I think I speak for everyone who was on the webinar in thanking you for your insights and for providing this information and talking about the value of these riparian forests and how to move forward, how to move the needle in the right direction. So it's really encouraging to hear your optimism with its scientific foundation that it is possible to have those things we need for humans and still have clean, functioning streams and healthy surface water. So really exciting possibilities ahead if we can focus on this and create that room for the streams themselves.
Well, it was my pleasure, Eric, and thanks for inviting me.
Yeah, great evening. Thank you, everyone, for coming. For those people that are still on, again, we will share a link to this webinar. And again, for everyone, Bern, thank you so much for your time this evening.
Okay. My pleasure.
All right. Good night, everyone.